there were these 3 exercises: tinyURL /neuron diffusion exercise /neuron regen signal, neuron Hodgkin-Huxley example 2, because we did some Hodgkin-Huxley stuff yesterday. Just start out with a diffusion and see what happens. These are a little bit more structured than yesterday. So if you go to tinyURL / whatever it was, it's going to give us some exercises, and these are going to step us through. So here's the idea. So let's look through, before we do anything, let's actually look through it. It's probably good advice. All right, we're going to want to load some libraries. That's cool. Pip install neuron. Yeah, you're going to need that. From neuron, import H and RxD. Now, if we're looking at chemical dynamics, yesterday was just H, but if we've got chemical, it's RxD as well. Cool. Units are our friends. STD run. Good old STD run. Right. I should have updated this. So my example here uses bouquet. It really doesn't matter. It's just a plotting library. Plotly's a plotting library. It so happens that I already have the code for plotting. So we're going to just leave it since I don't have to rewrite it. And you'll just use it. But in any case, we're going to load neuron, load our libraries. That's all boring. Load graphs, libraries. Create a section. Cool. Then what's it want us to do? Set a diameter, have a length. Add some species with a diffusion constant, have some initialization. This runs the simulation and plots it. And then so here's the deal. We start with a thing that's a square wave pulse in the middle, and then it's going to diffuse away over time. That's what we want to see. And then we want to be able to answer some questions. So when does a certain position exceed a certain concentration, and how big does it get at that distance away? Okay, you could imagine that 100 nanomolar might be the threshold that we need to trigger a regenerative phenomenon that's going to boost it up. So how long is it going to take to get there? And that we can estimate a wave speed if that was the case. So does the problem make sense? We want to study diffusion. We have a thing that's going to diffuse, and we want to know how quickly it reaches a certain threshold and how big it gets. Okay? So by the way, so when you do this, the easiest thing to do, the way that I would do this is I would just go File, Save a Copy, and Drive. Actually, let me lie. The way that I am doing this is I'll go File, Save a Copy, and Drive, and I'll just open it. And then so now I'm working, now I'm working in my own copy, so I'm not going to mess anybody else up or anything like that. And you can do the same thing, and then you have your own copy. So, okay, so pip install neuron, load some libraries, load the graphics libraries. Again, bouquet, matplotlib, plotly, whatever, it doesn't matter. But since the graph code is already here, let's just use bouquet since it's already in there. Is that okay with everybody? Okay. It's the same exact type of graphs we did the other day. Start with this section. All of this makes sense to everybody so far. It's all stuff we did yesterday, except comma RxD. Cool. All right. Set the dendrite to have a length of 100 microns. That's easy. How do we do that?
Den.L.
Den.L is 100 microns. And I did import 3 microns. Cool. Here's a question for you. If I'm talking about concentration and I'm fundamentally one-dimensional, do I actually care about the diameter here? There's no ion channels involved in this particular model.
So we need the volume, right?
Well, it defines a volume. There is a diameter, right? But is there any difference between if I'm not looking at things that are coming into my volume across the surface area, because then all of a sudden the surface to volume ratio matters, right? But if it's just chemical and it's just inside and it's 1D, do I care what the diameter is? I actually don't. You can do that as an experiment, though, if you don't believe me. You can try the diameter of 1, try the diameter of 500. And you'll see in that case, it's the same thing. If all of a sudden you start adding ion channels, that's a whole nother can of worms, and then it will very much matter. All right, so dendrite has a length of 100 microns. Cool. I'm going to add a species with a diffusion constant of 1 square micron per millisecond on that dendrite. What do I need to do to add a species? There's a hint here.
We'll define a region, right?
Right. So let's say the cytosol. And how do I define the cytosol?
RxD.region, and then you pass it the dendrite.
Yeah, so it just lives on the dendrites. I don't think I care about any of the rest of the parameters, but I'll go ahead and give it a name because it's always nice to have things have names because then they print out all pretty. And it's easier for debugging. All right, so I have a cytosol, and I'm going to have a species. It's going to be IP3. It's going to be a species that lives on my cytosol. It's going to have a, what did I say? It's going to be a species that lives on the cytosol. It's going to have a name of IP3. It's going to have a diffusion constant of 1. If I was lazy, I could just say 1 because square microns per millisecond is the default. But let's go ahead and be explicit. And yeah, both of those units are defined, so we're all good. I have a species living on that. All right, that would do it. Actually, you know what? That'll do it. Let's just leave it. Would I have it? Yeah, go ahead.
Sorry, just so the initial concentration, that's sort of at the beginning of the section.
So, well, okay. So, that was what I was hesitating about. So the initial concentration says initial in the sense of time 0. Right. So if I know where things are at the beginning and I know how things evolve, then I know everything. So initial is going to be across the entire length, and what I said here is between positions 40 and 60 microns, it's 1 millimolar. Otherwise, it's 0. Okay. So I'm going to need to set the initial value here. And it's a non-uniform initial. If I had the function handy, I could have gone ahead and passed it into comma initial equals and then the function. But I haven't written it yet, so that's mildly inconvenient. So let's just run this as is. And then so now I'll say, let's define this. So here's my initial, or let's say IP3 in that. That's what I want it to be, right? And it's a function that lives on a node. It's going to take a location, and it's going to return a result. And I'm saying between 40 and 60 microns in, I want it to be 1 millimolar. Otherwise, I want it to be something else. How do I say between 40 and 60 microns in?
I mean, if this works like the segments on a section, does it?
It does.
Well, then you give it 5 segments, and you set it to, what is it? 1 millimolar in the center and 0 elsewhere.
Okay, but then it's not going to look like a square wave pulse. It's going to be up, down. So let's be a little bit more aggressive about it. Let's say there's 101 segments, because otherwise we won't have the resolution. We saw that last night. Okay.
I'm sorry, I have a question. So we didn't define the location of our dendrites. We just defined the length. So, I mean, either we consider like the normalized length, and we just say like in between 0.6 or sorry 0.4 and 0.6. The normalized length, we can put the initial concentration, or I don't know.
Yeah, I did mean this relative to the dendrite. You're right. In potential, it could be here, it could be here, it could be over there, it could be any of a number. So right, so we're going to have to measure that. The only way it makes sense is if it's relative to the dendrite. We could do the normalized position. I actually like, for the sake of this, though, let's actually be different. Let's say, let's not use the normalized position, but let's say if 40 is less than 40 microns is less than h dot distance between the beginning of the dendrite and the node. Is less than 60. You're right. The node has a dot x, and then I could say if 0.4 is less than node dot x is less than 0.6. I just want to be different and difficult. But I wanted to show you this syntax, right? Like distance tells us the distance. Sometimes it is nice to think about distance. So if we're between 40 and 60 microns out, we're going to return 1 millimolar. Otherwise, we're going to return 0 millimolars. And that's going to be our initial rule. Does that function make sense to people?
Yeah.
And because I'm paranoid about this, did I define millimolars? No, I did not. Millimolars. Now I've defined millimolars. Otherwise, it's going to give me an error, right, when I try and do something. Because it's like, I don't know what that is. Okay, so where are we at? We've defined it. Oh, yeah, we haven't set the initial value. Like I said, we could have passed this in as a keyword argument, but you can do it just as easily after the fact by setting initial equals. Dot notation. Does that make sense? IP3 in it. So we've specified.
Robert, wait a minute. IP3 is the name of the species, right?
Yeah, it was up here.
Yeah.
And well, okay, minor pedantic point. IP3 is the variable name. That's what's important, not the name. But yes. Inositol triphosphate comes up in calcium story. All right, so does this make sense? We defined a region, we defined our geometry has a certain length, we defined cytosol lives on it, IP3 lives on the cytosol, diffuses at a certain rate. We said that we need an inseg to be big enough in order to actually see a change. We defined a rule that says if we're between 40 and 60 microns from the 0 end of the dendrite, it's going to be 1, otherwise it's going to be 0. And we said that that rule was our initial value. Any questions on any of this? All right, let's see what happens.
So in that function, do we not need to input, like place IP3 as the kind of like input to that function?
No, because it's no.
Okay.
The node. So that is one of the other differences between a node and a segment. The node knows that it's associated with IP3, and it's only used to initialize IP3.
Okay.
So it doesn't care. Does that make sense? All right, so we run it, and sure enough, we get what we expected to get. We have a pulse, it diffuses, blah, blah, blah. What if instead, just for giggles, what if instead I were to change the diffusion constant? What if the diffusion constant, that's IP3.d, I believe. Yep. What if the diffusion constant was 2 square microns per millisecond? What's going to happen? Hypothesis. I haven't run it.
Wouldn't our variance just get larger just because the curve's going to flatten?
Let's find out. Sure enough. All right, let's go back to a diffusion constant of 1. Well, let's go back to a diffusion constant of 1. All right. So, but we can easily go back and we can play around with it. We can make changes, is my point, right? We can do sweeps. We can do these experiments. We can do these what-if questions. So here's my question for you. When does position 70 microns exceed 100 nanomolars? It's pretty fast, right? Because it's only 10 microns away from the edge, where it's 1 millimolar. So 100 nanomolars is not much. It's not going to take long. But when? When does it exceed 100 nanomolars? And what's the peak? And how would we find out?
Spread the window.
Sorry?
You'll spread the window.
You mean like zoom in on the graph?
No. Like right now you have 40 to 60, right?
Right, so here's 40, here's 60, and here's 70. So in particular, it's sometime before 50 milliseconds, because at that point it's, I don't know, 0.1 millimolars. So it's well before this point. So I didn't plot this, and I know it's going to get up to at least 0.2 because it, you know, it's above 0.2 here.
Can we record the concentration? Like
Yeah, let's do that. So I'm going to want to record, if I'm recording, I'm probably going to want to record of time as well, right? So that's always going to be formulaic. I'm going to create a vector, and I'm going to do a dot record, h.refc. And then concentration, let's say. I'll have another vector. I'm going to record, what do I call it, IP3. So it's IP3, but where? It's IP3. I'm going to grab the nodes. That's going to be all of the locations, basically. And then I'm going to say, parentheses, which one do I want? I want the one at dendrite of 0.7. So this is using the normalized position.
And that's snapping to the closest, I guess?
Yes.
Okay.
But yes. So that's going to give me the right node. I mean, literally, it's snapping the closest. The way that I had it in my head was, it's the node that contains the 0.7 location, right? Because each one, yeah, but yeah, it's the same thing. So in any case, so then I want the, so normally the value would be dot concentration would be the current value. Well, in fact, let's do that. Let's do that. Let's just look at it right now. IP3 nodes at dend of 0.7, it's at 7, dot concentration. There's one slight surprise here. So right now it's 0.25. What's the slight surprise that you might see here? What might have surprised you about that? I mean, not the value at 0.7. It's, I believe that 0.25. I got no problem with that. But what do I think might have surprised you about this answer?
That it's a vector?
Yeah. Why do you think that is?
Yeah, it's less simulation point, I guess, because it's not reference. It's not recorded stuff.
Yeah. So this is the live. This is where we ended. But it's a vector because I can have. Remember, this doesn't necessarily uniquely define it. I have a position along the geometry of the cell, and I have a species. But it's not necessarily uniquely defined because this is, now in our case it is, because there's only one location where the species could be in the cytosol. But if it was in the ER, for example, I would want to filter that too. And this would give me, well, these are all of the IP3 concentrations at that location, but you got to figure out which one is which. Is it the cytosol? Is it the ER? But for us, we only have one, so it's no problem. And in the case where it's uniquely defined, if I grab a pointer, it's going to be the pointer to that location, and I don't have to index it. But if you did index it, it would be fine too. But so in any case, so it's the IP3 node at that location's concentration. And it's a pointer, because it's always a pointer. Anytime you do use a vector record, there better be an underbar ref somewhere. Okay? So, cool. We've defined it. Now I guess we run, right? All right, F initialize, negative 65 millivolts. Doesn't matter because we're not paying any attention to voltage. Nothing's using voltage. But we need to set it to something, so that's as good of a number as any. And then we'll run this until, I don't remember what I did, 150 milliseconds. We don't know that we've got the peak yet. So let's be bold. Let's run it to 1,000 milliseconds. It's probably going to flatten out by then. Okay, cool. We've ran the simulation. We have the data. Let's answer the last question first because it's easiest, ever so slightly. What's the peak value? Well, in Python, how do I find the biggest value in an iterable? Not a trick question.
Max.
Max. All right. What's the maximum value of the concentration that we obtain? 0.25. And the reason being because this is, as it levels out, it's going to come out maybe be about 0.2 everywhere. That make sense? So it goes up and then it goes down. And we could plot that if we wanted to. We could see the time series as it goes up and it goes down. And it wouldn't necessarily be a bad idea to do that. So then what about the other question, though? When does the concentration exceed 100 nanomolars? So how would you do that?
Oh, this is just a NumPy array, right? Or do we have to convert it?
Technically speaking, it's not. So fun fact, if you want an NumPy array, conc NumPy is conc.as numpy. And so while I'm at it, by the way, so this is the NumPy version. So that's the NumPy array thing. If I were to change the 0th value to 42, it's not 42, it's 0. So it's easy to remember. What do you think concentration of 0 is?
I mean, probably doesn't backpropagate, does it? Oh. Never mind then.
And obviously, it forward propagates as well. So conc NumPy of 0 is 0. So the point that I'm making here is it literally, so the name matters. It says as NumPy. It's not to NumPy. There's no conversion. It's literally the same block of memory. It's just different ways of accessing it. You can access it using the neuron interface, or you can access it using the NumPy interface. But it's the same memory. It turns out you almost never need the NumPy interface, but you have a NumPy solution for me?
Oh,
Because there was a question we were trying to answer.
right. Well, can you just do NumPy where, and then find the first index where it crosses the 10 nanomolar?
Okay, let's see. So what's the deal now? NumPy where conc. Wait, how does this even work?
Oh, you would basically ask, right? So sorry, we're asking when it. Oh.
It says that nanomolars was not defined, which is certainly true. I did not import nanomolars.
Right, and so the first index would be the index of the times, sort of the earliest time point at which we've seen it go above.
Okay. So that'll work.
All right, I assume there's an easier way.
I don't know. I mean, it depends. If you know this is very easy. I clearly do not know that. The naive way to do this, I mean, so you could literally just loop through everything, right? And I'll just loop through for, my T and my const and zip of T and const. If my const is more than 100 nanomolars, friends, crossed at T equals my T milliseconds, and then break. So we just loop through everything together, find the point where we cross, and say it. Either way, we come up with the same number. I'm 100% certain the NumPy solution is faster. But
It doesn't really matter at that, you know.
yeah, I mean, so it's all a question of what you consider readable, what works for you. But in any case, we've answered it. We've answered it 2 ways. We got the same answer. That's always nice. Does anybody have any questions on that? Oh, I guess here's an interesting question while we're at it, though. When do we get to that peak? So here's the peak value. So numpy.where, and I think we don't actually, well, yeah, maybe we do, is equal to the peak value. Just because I'm curious. 6,000. So there you go. So we hit the peak at the 6,000th time point, which is 150, that explains it, 150 milliseconds in, and then afterwards it starts to decline. And if we wanted, we could plot this and see what it looks like. I don't know if that's worthwhile or not, but it goes up and then it goes down. Is that intuitive, or should we plot it?
Go for it.
All right, let's see. Import plotly.graphObjects as go. I said as go. Fig is go.figure. Fig.add trace. Go.scatter. What is it? X is equal to T. Y is equal to concentration. And that's it, right? Fig.show. So here's the concentration over time. It goes up. It peaks around 150. Well, it peaks at 150. And then it starts dropping. And basically, the concentration starts leveling off everywhere at about 0.21. Well, actually, we know exactly what the concentration should level off at eventually. What is the limit as t goes to infinity of the concentration of, in this is an actual problem, assuming that, you know, forget the numerical approximation wherein, you know, are the nodes just to the left or just to the right? But if we actually solve the problem, what is the limiting concentration? What happens? Okay, I have a system. I let it diffuse for infinitely long. How different is the concentration here from the concentration here?
Not at all.
Not at all, right? So the limit is that it's a uniform concentration. Matter is neither created nor destroyed. We start with between 40 and 60 being 1 and everywhere else being 0. So our total amount of mass is basically, well, our average concentration is 0.2 millimolars because it's 1/5 of it is 1, everything else is 0. So the limiting concentration is going to be 0.2 millimolars as it averages out. Does that make sense? Well, I mean, it's just good to try. And the reason that I asked you this is because it's good to try and have intuition for things, because if you don't have intuition for things, you don't know if your answers make any sense. And if you don't know if your answers make any sense, that's probably not a good thing. All right, any other questions about this exercise? All right. So we have, that was the pure diffusion. We've got a regenerative signaling one and a Hodgkin-Huxley concentrations and homeostasis one left. Any preferences? Number 2? Okay.
Well, I feel like I feel bad that I'm always the one sort of, you know, making a wish. Maybe somebody else wants to.
Anybody else have opinions, preferences? I mean, we'll try and do all of them, but what's this?
I like 2, yeah.
The middle one?
Yeah.
It's tricky because the last one, the third one, has a 2 in it. So yeah. So the second one, altogether. Okay. And again, we're going to start out, and I'll just make a copy of this, and I'll work on a copy. Okay. And by the way, was everybody here able to find the solutions from last night? So they're in the code folder. Okay. So here we go. So regenerative signaling, we talked about regenerative signaling a little bit with calcium waves. Calcium waves involve multiple factors. You might have, so the story that we told in that paper that I alluded to has an IP3 receptor, which has its own states. It's got a circuit pump, which is sequestering calcium into the ER. There's a leak channel between the ER and the cytosol. And so you end up with several states and different things, and it's rather complicated. But we can sort of collapse this down mathematically, at least. Here's a nice little simple system that's going to generate the same kind of a dynamics that we might see with a calcium wave. So what we have here, this is the diffusion term, right? The partial of y with respect to time is proportional to Laplacian. It's just diffusion. It's the same thing as the cable equation. And over here is the reaction. So tell me this. Most of you guys have taken DiffyQ, is that true? Okay, I'm looking at least some nods. So pretend that there's no diffusion for the moment. So we'll take away the Laplacian. And then this is just a regular time derivative, ordinary differential equation. dy dt is equal to negative ky alpha minus y, 1 minus y. What can you tell me about the qualitative solutions as t goes to infinity of that differential equation, of that reaction system, of that differential equation?
Would it be exponential?
Would
it? I mean, I would think so. Wouldn't it just be separable? And then it's just a first order if you say your diffusion is 0.
So it's certainly a separate, yeah, it's certainly a separable differential equation. That is true. What about fixed points? Fixed points are always the first thing that I look at when I see a differential equation. What can you tell me about fixed points?
Clearly, without diffusion, they're gonna be 0, 1, and alpha or a. What it is.
Yeah. Right. If y is 1, then the derivative is 0. If y is alpha, then the derivative is 0. If y is 0, then the derivative is 0. And then you can do that. What is it? The first derivative test or the second derivative test, either one, and talk about stability of fixed points. Hopefully, this sounds vaguely familiar to most of you. If it doesn't, at least you can see, well, nothing changes if it's 0 everywhere. Nothing changes if it's alpha everywhere. So the system wants to be at these 3 values. And if alpha is between 0 and 1, the stability is such that 1 is a stable fixed point, 0 is a stable fixed point, and alpha is an unstable fixed point. You can prove that to yourself with the first derivative test if you are so inclined. But in any case, so the system wants to be either at 0 or 1. And so when I add diffusion and I start with a pulse, it's gonna diffuse a little. So I have a pulse. I have a from all the way back up till here, it's 1, let's say, and then it drops to 0. A little bit of diffusion is going to bring down the high part. It's going to bring up the low part. Does that make sense? If I go above the threshold, above alpha on the low part, then the low part's going to want to go up. If, on the other hand, the high part drops below alpha, then it's going to want to go down towards 0. Fixed point stability. All right. But imagine those words, but also the word calcium. Okay, so we have a hypothesis. We think we know what's going to happen. We've reasoned through it. Let's see what actually happens. That's my prediction. That's our prediction. So here we do. We set everything up. We're going to install Neuron. Cool, cool. Here I've gone ahead and set up for you a geometry. So it's a section. It's going to have a certain length, a certain diameter, a certain inseg. Diameter is 500, length is 500 microns. Diameter is 2 microns. Units are nice. Yeah, by the way, so Neuron is perfectly happy with both UM and UM. If you're on a Mac, option M is how you type mu. If you're not on a Mac, I don't know, but it can be done. But in any case, all right, fine. So here we go. So we define a region. We've got our species. We've got a parameter of K and a parameter alpha, right? Because these are parameters. These are numbers that are describing the shape of the system. And I may want to go back and do a parameter sweep. I may want to see how things change. So I'm not going to hard code them in as numbers. I'm going to define them as parameters. Heck, I don't even need them to be the same everywhere. Could change along the line, right? Some property of the excitability of the cell could be different over here than it is over there. Maybe there's more IP3 receptors. Actually, in fact, IP3 receptors we think tend to be clustered. So there you go. There's clusters here, high density here, low density there. All right. So this is going to be very similar to what we just did. Set the initial condition such that Y is 1 millimolar to the left when no.x is less than 0.5 and 0 elsewhere. Again, remember, we just define a function, right? My initial, I don't know. Let's call it why not. Why not? Of node, if node.x is less than 0.5. Remember, .x is the normalized position. It's not a real position. Okay. If node.x is less than 0.5, we return 1 millimolar. Not 1 map. Else return 0. Cool. Do I define millimolar above? I did not. That would be 2 millimolar. Cool. All right, set Y initial. Oh, I hadn't actually set Y initial. So I've defined my rule, and then I'll actually set it. So Y dot initial is going to be Y naught. Cool. Define the rate rule using RxD.rate. Be sure to save it to a variable. So here, I mean, since I only have one variable, I'm just straight up going to put in the differential equation reaction term. It's not going to be. It's not that calcium is becoming something else, right? We can have a reaction that does that. But in this case, we really don't. It's just, it's changing according to these rules. And sometimes that's what you have. If you've taken a paper from a mathematician, they write down a differential equation for you, and that's what you got. So that is to say that, I don't know, dy is going to be RxD.rate. Y is the thing that's going to change. It's going to change by an amount negative k times y times 1 minus y times alpha minus y. Why does it change that way? Because that's what we were told. That is the dynamics that we have decided that it is, right? We started with that problem. That is our model, and we are just implementing that model. However we got it, right? I'm making that a separate problem right now. However we got that model, we're implementing it. Does that make sense? Okay. By the way, one thing, and I haven't really made a huge point about this, you'll notice that every time I define something, I throw it in a variable. The general rule with Neuron and Python, for that matter, is if something's not in a variable, it doesn't exist. Python does what's known as garbage collection. This is a gotcha for some people. Don't be one of those people. Store everything in a variable. Don't, if you define something in a function, make sure you return that thing, that variable that you defined. because otherwise it won't be available when the function ends, and then it'll get garbage collected, and then you won't have your section. All right, just return it, throw it to a global. I didn't say anything about globals. Don't use globals. Globals are bad. All right, so plot the concentration of y versus position at several time points to show the development of a traveling wavefront. You know what? We did this in the last exercise. We actually had the code in the last exercise. Do you want to borrow from the last exercise, or do you want to try the plot? Let's just borrow from the last exercise. I'm seeing shrugs. So what was our last exercise? That was diffusion exercise. But really, we did this yesterday. It was one of the exercises yesterday, right? We did it with Plotly then. Here we're using bouquet, and that's why I'm being lazy and borrowing from the previous exercise. But cool. Does this code make sense, though, in general? There's nothing here. I'm initializing it. I'm plotting it between here and here. I'm defining my figure. I'm running my simulation until various time points. I'm drawing at different colors. By the way, these parameters may look different from yesterday. Why do they look different from yesterday? Because yesterday we used Plotly, and we plotted on a Plotly object. Now we're plotting on a bouquet object, and we're using whatever keyword options are available for bouquet are available for. Basically, RVP.plot is going, rangevarplot.plot is going to try and do the right thing for whatever type of graph you give it. If you go out of your way to find some weird graphics library, that's not my fault. But it tries to be aware of as many things as possible. So how did I lose the one that we were working on? Okay, well, that's how I lost it. Okay, so boom. But instead of plotting IP3, we're going to plot Y. Oh, the one other thing that I'll point out, you'll remember that yesterday when we were doing this with rangevarplot, we were using strings. But here, if it's an object that's defined with RxD, I can just pass in that object. And this is, I don't know, saves me 2 characters. So cool. We'll plot Y between, is it din still? It is din. We'll plot Y from din 0 to din 1. We'll run it to a bunch of time points, and we'll see what happens. Okay. So maybe not as much movement as we thought, but x-axis is position. Each line is a different color. So we start out at the black line, then we went to the 50 milliseconds, 100 milliseconds, 150 milliseconds. So we do have a thing that's moving. And it's moving that way. It's moving in the direction of small is becoming bigger. Does that make sense as a concept? Okay, so it says run the same simulation with alpha value of 0.7. By the way, what was alpha before? Alpha had a value of 0.3. So that's easy. Alpha.value is now going to be 0.7. You could imagine that you could do this in a for loop if you were doing a parameter sweep, right? Cool. And then I'll literally copy paste the code, and it's not IP3, it's Y. And I'll literally copy paste the code correctly. And so it's going to look very similar, except look at the direction now. We started at 0, and then we collapsed. We had a collapse to 50, a collapse to 100, and a collapse to 150. Now, if you think about this, remember there's 2 stable steady states. There's a stable steady state at 0, there's a stable steady state at 1. It's either going to want to go all towards 1 or all towards 0. And so why is it that alpha being 0.3 led it to going towards 1, and alpha being 0.7 led it to be going towards 0? Hypothesize.
Can I make a question?
Please, please.
Why, when we are updating the alpha value, we don't just redo the account again, the model account again? We just update the alpha value.
Oh, you mean why didn't we just rerun everything?
No, just the equation where we just set the equation that we use it as a model.
Oh, this line?
Yes.
Why
Yeah,
didn't I
this
just hard code 0.3 and 0.7?
Yeah.
Two reasons. First of all, since it's a parameter, it can vary spatially, and so it gives me the flexibility. I mean, we didn't use that, but like a thing that we could have done, we could have imagined in some part of the domain the dynamics are different than they are in the other. But that didn't apply to us. You're absolutely right. So we could have hard-coded it here, and we could have reran it, and that would have worked just fine. The one caveat that I'll give you with this, and because the old one would be garbage collected, because it wouldn't exist anymore because it's assigned to the same variable, so there's no problem there. The one caveat that I'll give you with this is that the way that this actually works behind the scenes is that in order to, so we're writing in Python, and it's very easy for us to think in Python. Python is not what we call a fast programming language. And so that the way that Neuron's able to do things quickly is that Neuron itself is written in C. All of the calculations it does are written in C. What that means is it takes this expression, and behind the scenes, it has to compile it to C. This is not a big deal. It happens relatively fast. Nonetheless, if I just change a parameter value, I don't have to recompile everything. Yeah, that's the only real advantage. But it doesn't make that much of a difference. But
okay, thanks.
Yeah. Any other questions or comments on this? All right. And so, like I said, you could imagine how this extends to 3 dimensions. You could imagine how this extends to calcium waves. We've got a model on ModelDB. You can go and play with the calcium waves. Actually, we have a model and read the docs, I think, for calcium waves. I think we do. I'm going to end up read the docs. Just curious what's actually up there. Calcium waves, that sounds promising. Well, we have part of a model and read the docs, but we have a model in ModelDB because it's published and it exists. Okay. So if there's no questions on this, let's go and see if we've got, I think, 14 minutes before the session officially ends. Let's see if we can get, let's see what we can do on the Hodgkin-Huxley and how that plays out. So, where is that? Neuron HH example. Let's make a copy of this. Okay. Blah, blah, blah. Install Neuron, load the libraries, load the units, load std run. No surprises here. This is kind of formulaic for us, right? Load a graphics library. I don't know if I'll use Bokeh. I may end up falling back to Plotly, but we'll see. Here's a model. We're going to have an axon. We're going to insert Hodgkin-Huxley channels into the axon. The axon is going to have a certain diameter. It's not going to be very long, but that's okay for this case. All right. Is this code readable to everybody at this point? There's one compartment. I'm not going to bother with creating a segment, a discretization. I could, but I don't need it for this exercise. It's small, right? It's 10 microns long. I don't. It's small. I'm going to add a current clamp. It's going to be at the center of the axon. It doesn't matter where it is. There's only one compartment. Nonetheless. there's a current clamp at the center of the axon. It's going to have a certain amplitude, nanoamps, certain duration, and a certain delay. Again, I hope all of this is very familiar. How this is expressed in pure NetPyNE is slightly different, but fundamentally, these are the questions that you need to answer, right? How much juice am I giving? When am I giving it? And when do I stop? Right? So in pure NetPyNE, it's going to look slightly different, but it's the same questions. If I want to record, I know I need to record time. It's always a good idea to record time. And the membrane potential, that's cool. I can run a simulation, -65 millivolts, initial conditions, and I'll continue to run for 10 milliseconds. By the way, obviously, this is now Hodgkin-Huxley. This now has a membrane potential. So the choice here for -65 actually does mean something, right? It does make a difference. But in any case, I run it, and I can make a pretty picture. And there's current that's injected. The membrane potential goes up, and then a spike, and then it goes back down. And this membrane potential, the first exercise we did yesterday was potential across space, and so it looked a little different than this one, which is potential across time at one point. But this is probably the way most of you are used to looking at membrane potentials. So far, hopefully no surprises, but I'll, with that nasty prelude, is anybody still willing to ask questions after that? Okay. So we've set up a thing. Modify the above to use a constant current. I have been told that that's ambiguous, by which I mean a current that stays on for a very long time. A constant current that causes a cell to fire periodically. How would I change this to have the cell fire periodically and also obviously see that it does so? What needs to change? Logically.
On the current?
What on the current?
The delay, or yeah, the delay. You can make a bunch of different clamps and then change the delays.
I could do that. I could change. I could, however, have the current clamp stay on longer. I could change the duration as well, right? Is that you good with that?
Yep.
Why do more work than I have to? So there you go. I changed one number, and I'll rerun that cell. It would have sufficed to just say IC.dir, but I didn't. So, oh well. So now if I initialize and run this and plot this. Okay, well, there's two things that we see here. Thing number one, I didn't run it very long, so I can't really tell what it's going to do. But you see something already that looks like it's going to be a problem. What looks like? What's this?
Oh, I was just going to say that it's not hyperpolarizing.
Yeah, well, it's not depolarizing either.
Well, is that because it never hyperpolarized, and the channels didn't get out of the refractory period?
Yeah. So first of all, let's run this longer just to see what happens. But you're absolutely right. So we get false starts, and it gets worse and worse, and then the cell just stays depolarized, but not firing action potentials. So what is the solution? What caused this, and what's the solution?
We should probably decrease the amplitude of the current injected.
I agree. Let's see what happens. So instead of this, let's decrease it by a factor of 1/2. And run it. Okay. Still kind of sad looking. But if I were to zoom in, I said if I were to zoom in, it's definitely periodic, right? They're action potential-esque, but they don't quite make it. So maybe that's still too much. Let's drop it some more. Okay, that looks more promising. It's firing pretty fast. I mean, it's boom, 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 boom. But it's firing periodically. Maybe we go a little lower still. I guess that's a factor of 4. That might be a lot lower. We'll find out if that's enough. All right, all right. That looks like an action potential-ish. What do you think? We happy enough with those? Okay. So that was incidentally one of those things that it may have been, if you didn't think about the biophysics that's underlying it. It's not spiking. I need to hit it harder. No, you didn't. We need to hit it less. So, all right. So in any case, we've done that now. It's a cell that fires periodically. Cool. And the first one looks a little different, and technically so does the second one, but it's approaching a limit cycle. You buy that, it's gonna be fine. So we've done that. Verify that intracellular sodium and potassium are constant in this model. How can I do that?
We should record the NaO and potassium intracellular. I don't remember how it's written. Probably Ki, exactly. We should record those concentration of it.
Yeah, go ahead. I'm sorry.
No, just that. Record the concentration over time.
One minor point, it's NaI because it's the concentration inside the cell, not the concentration outside the cell. But your point stands. So Na for sodium, K for potassium. That's why it is what it is. So here's that. So we've recorded this, and then we would run the simulation, and then we would plot it. So H dot initial line, 65 millivolts. Cool. H dot continue run until, I don't know what I did, 1,000 milliseconds. And cool. And let's just plot them. Let's say. You can plot them using whatever you want. I'm just using bouquet because I can copy paste. And it's already on my page. So here's concentration. And this is going to be measured in millimolar. And I'll plot I'll plot NaI, and I'll give it a color of red and a legend label of NaI. Cool. And I'll add another one for potassium, Ki. We shall call this blue. Ooh, that's a nice color scheme. Red makes it go up, blue makes it go down. That's cool. All right. Well, it certainly looks flat, but I mean, it might not actually be flat. I don't know. How could I prove that it's flat? Like, as opposed to, you know, ever so slightly off.
Look at the start and the end values.
Well, I better not do start and end because I don't know that it didn't, you know, bump in the middle.
Oh, min and max?
Yeah. So let's see. Is the minimum of NaI equal to the maximum of NaI? Why, yes, it is. Is the minimum of Ki equal to the maximum of Ki? Why, yes, it is. And as a sanity check, anytime that you're doing something like this, let's make sure that we get an answer that's other than, you know, that we can get a different answer besides true. So what's something that we know should be false? Is the minimum of Ki equal to the maximum of NaI? It better not be. Okay, good. This seems like a thing that might work. But you know what I'm saying? Like, it's good to have this test so that all your answers aren't all the same. And you're like, okay. Anyways, so we've shown that the concentration is literally constant. And so my point is, however, if we monitor this using the reaction diffusion, then now all of a sudden we wouldn't expect that to be the case. And this is small enough of a domain. It's not a squid. It's small enough of a domain. We should see a real change. So let's see what happens. So how do I declare these things? What do I need to do? I mean, this is the part that's the actual reaction diffusion part. What do I need to do?
You can write NA equal to RxD species, and then yeah, we need to define the region, something that we didn't do so far.
So I'll create a region. If I'm doing it, if it needs to interact with the ion channels, then it has to have a neuron region. It has to be the just inside part. So I do need that. And again, for debugging, it's nice to have a name. It doesn't change the kinetics in any way, shape, or form. It doesn't have any meaning, but it's good for us for debugging. Hopefully we don't make mistakes, but you know, it's there have been times. So I'll define it. It's a species that lives on the cytosol. It's going to have a name. Here, the name does matter because otherwise it's not going to be able to map it to NAI, right? It's not going to map it to the sodium currents. And so this has a charge of 1. And likewise, I'll have a potassium is a thing that lives here, and it has a charge of 1. So I've not imported RxD. From neuron import RxD. That's okay. Error messages mean something. It's not called DEND. It's called axon. Okay, so much for not having to debug. Did I make any other mistakes? All right. Okay, that's a good sign. So now, how does this change the answer to the previous question? Well, let's look at it. So let's run the simulation again and see what happens to potassium and sodium. Right? Does that make sense? That's the next step. All right. So F initialize, negative 65 millivolts. Continue run 1,000 milliseconds. Obviously, you know, if this was really our protocol and we wanted to run this over and over again, we'd put this in a function, right? And we'd only have to type it once, but we didn't. So we're dealing with it. Well, that's interesting, isn't it? That's different. Well, it makes sense, right? Membrane potential goes up because sodium's going up. So that means literally sodium goes up. And potassium is leaving the cell, so potassium concentration goes down. So that's interesting. So then what does this mean for the voltage? Any hypotheses? I see hand gestures. What is it? Somebody want to translate that into words?
It goes up.
Let's find out. I mean, we've already recorded it. We don't even need to rerun the simulation. We just need to make the plot. So let's do it. We're going to plot voltage. And this will be voltage. And this will be voltage. Nope. In millivolts. Again, matplotlib, whatever you want. All is well with the world. How does that compare to your expectations? But if you think about it, here's a rationale, right? Sodium in the inside is becoming more like sodium on the outside with every action potential. Potassium on the inside is becoming more like potassium on the outside. So the amount of swing that we're going to get by opening the channels is less and less every time. And so we get these damped oscillations. And then eventually, let's say that instead of running it to 1,000, we ran it to 10,000 milliseconds. And let's see what happened. Are you going to be mad at me for plotting all that? No? Okay. So,
Robert, sorry.
yes.
So it was supposed to finish like at 3:20, but the other group is also still going. So we're gonna do like 15 more minutes, and then we'll delay everything.
We'll definitely be done in 15 minutes. No problem.
Okay, great. Thanks.
All right. So potassium is approached. Potassium is basically flattened out. It was the first to flatten out at the extracellular concentration. Sodium hasn't yet, but once potassium flattened out, you're not getting any action potentials. And then you get this depolarization of membrane potential. So they collapsed. We had damped oscillations until it collapsed to a point, and then it got even weirder. But then it just stayed as damped oscillations. So from a physical standpoint, what does this mean? What would cause this? What would cause this problem? I already explicitly said it earlier in the lecture. But
The concentration outside and inside the cell.
Right. So yeah, I mean the key thing about a cell, the key thing about biology is that it maintains some state that's different from the outside. And when it stops being different from the outside, that's a problem. So we, like I said, an ischemic stroke, which blocks the flow of oxygen, would cause ATP to fail, would cause the pumps to fail. The pumps would not be able to make up for the sodium-potassium difference. Okay, so then, and this is the final question in this whole set. How can we fix this? What would be a simple homeostatic mechanism? And I'm not so ambitious as to do a full sodium-potassium exchanger because it's going to...
A pump?
Yeah.
It's a little bit slow, a pump, right?
So, okay, so a pump... Okay, so talk to me about it. Okay, so there's a reason that I don't want to do a full sodium-potassium exchanger. What's the stoichiometry of a sodium-potassium exchanger? Does it move the same number of sodium ions and potassium ions?
I think it's, maybe I'm wrong, but 3 to 2? Is it 3 to 2?
Yeah, it's 3 to 2. What's the stoichiometry of an action potential, basically? Let's say there was no leak channels. In a world where there was no leak, what would have to be the stoichiometry? How many sodium would have to come in and how many potassium would have to go? What's the relation?
I'm not pretty sure, but it's around 10,000.
Oh, okay. So
no,
this I have no idea actually in terms of the actual number of molecules counts. I'm happy to believe you, but I have no idea. What I meant was if sodium makes it go up and potassium makes it go down, and we end where we started, what's the relationship in sodium and potassium?
2 to 1?
Will it go up by an amount and then go back down to the same amount? Wouldn't it have to be 1 to 1? So we need as much going in as going out. Now there are other channels and biology is messy and there's lots of complications, and so this is a bit of a lie. But as a rough mental guideline, we have 1 to 1. So if I just do a straight up sodium potassium exchanger, that's the actual thing. I've got a 3 to 2. Well then, okay. Well now I still have to deal with now I have an imbalance because I can clear at a different rate than And then, so then that becomes a can of worms, because what else is going on? Well, there's also a calcium, you know, there are other pumps and there are other things that make up this homeostatic mechanisms. And let's just say that I'm being super lazy. Let's just say that the super lazy, the simplest model that I have is that over time, things are going to go back to where they should be. And I don't care about how exactly it gets there. I'm just going to say that over time, things are going to get where they need to be. Let's say, and I can quantify that, let's say for the sake of giggles, that there's a time constant that's associated with this. There's a time constant of, I don't know, 10 milliseconds, which is a number that I totally made up and has no known relation to biology, so don't use it for your models. Look it up. But suppose, for example, that potassium went back to where it was with a time constant of 10 milliseconds. How would I write that? So I have...
so would that be a multi-compartmental reaction?
It could be. It could be. I'm trying to be extremely lazy, and you're not letting me be lazy. So yes, the right way, especially with a pump, is a multi-compartment reaction. I believe we have some examples in the tutorials. If not, I can check. We certainly have examples floating around of doing exactly this. Before we go that complicated, I was just going to do it straight up with a rate, with a reaction rate. If I'm just going to think in terms of differential equations, is that cool? You're right. You're absolutely right. But I'm trying to end before Salvador chases me out. Okay, so let's say that we do it with. But this, by the way, is what that second question is. How does your mechanism compare to a sodium-potassium exchanger? We've really sort of discussed this now with length. We're cheating a lot. We're making simplifying assumptions. We're not cheating. We don't cheat. But it's how much detail do we feel needs to be in our biological model, in our conceptual model. So here we go. Sodium homeostasis mechanism. It's going to be a rate. There's some rate, RxD.rate, that's going to affect sodium. Okay? Everybody agree with that? Sodium is going to be changed somehow. How? Let's say that it has a time constant. Na tau is going to be 10 milliseconds. What should be the formula for a reversion to the baseline sodium concentration?
-1 on Na tau. -1 divided Na tau.
Well, I mean, so this is going to, but this isn't going to force us to go to a specific value. It's going to decrease at the time constant. You're absolutely right about that. Divided by Na tau, agree. But how do I get it to go to a specific value? So what is in squid, because we're using Hodgkin oxide, what is the value of sodium that we want it to go to? Because this will eventually go to 0, right? As t goes to infinity, this will go to 0. But what should squid concentration be, sodium concentration be?
The initial concentration.
Yeah. Well, here you go. Here's the picture. So 10 millimolars is a typical squared intracellular sodium concentration. 54.4 millimolars is a typical squared potassium concentration. All right. So that means that instead of that, we'll write this as, and let's see, with 10 minus Na. Let's see. So this is our differential equation, right? Na is going to change by a rate of 10 minus Na divided by Na tau. This is Na infinity, right? This is exactly the same formula that you use for gating variables, right? There's a limiting value minus the variable divided by the time constant. So it's exactly the same formula that you use in Hodgkin-Huxley. All right, so there's the sodium. And then the sanity check. If Na is bigger than 10, it's negative and it goes down. If Na is less than 10, it's positive and it goes up. So good. So I put the sign correctly. Because I screwed that up earlier on something else, remember? So potassium, same deal. Let's say that the potassium homeostasis is going to look exactly the same, and it's going to have its own time constant. It could be 10 milliseconds too, I don't care. So these are two mechanisms. I'm not really describing, yeah, you're right, there's an exchanger, but then there's actually several exchangers, and maybe there's ion-specific leaks that allow us to sort of balance out the imbalance of the different stoichiometry of the sodium-potassium exchanger versus what's going on in action potential. There's a lot of biology that we're not doing here, but all we're saying is by some mechanisms that I wash my hands of, sodium is going to go to 10 millimolar concentration at a certain rate. Potassium is going to go to 54 millimolars concentration at a certain rate. So that's our rule. And now let's just go back and rerun it. So here you go. I'm just going to be really lazy. Copy, paste. Again, the right thing to do if you're doing this would be to make a function, but, you know, far be it from me. So let's see what happens. Well, 10,000 is going to take a while. That's too bad. 10,000, we might not see a whole lot. Well, let's find out. Come on. Come on. I see you, like, you stopped spinning. Why did you stop spinning? Okay. We're not going down and we're not going up. You'll notice it looks really thick here. Let's not do 10,000. Let's do something shorter. So it's stable, right? It's stable for 10,000 milliseconds. I don't know for a fact that there's not some degree of perturbation and some degree where it's going inching up ever so slightly, but it's pretty stable, right? We basically fixed it. What is happening? Computer, stop. What are you doing? You're mad at me about that 10,000 points on you. I'm sorry, computer. Come on, come on. Instead of that, let's just look at what happens in that first 100 milliseconds. There's a little bump, and it goes back down. There's a little bump. We still see that. We still see the increase because there is an increase still in sodium, right? It's a very transient effect in sodium. It's a very transient effect in potassium. But our homeostatic mechanisms are able to compensate and restore it. And so that little bump just goes away. Any questions or comments on this? How do we feel about this? All right. Well, so then this is actually my my last session for this course. I do intend to be there on June, whatever day it is, for people's presentations. But I thank you for coming and for working for your enthusiasm. I'll be on Slack. I mean, at me if you want to get my attention. But otherwise, it's been great meeting you, and I wish you all the best.
Thanks, Robert.
Thank you. Thank you very much.
Thank you.
Thank you, Robert.
Thank you.
Thank you.